start recording. Let me put that away. Okay, I'm going to start with where I left over last time. I think I finished. Can you see my slides right now?
Yes.
We're done with the precipitation reaction. Okay. Last thing I want to talk about precipitation reaction is they are based on the idea an insoluble salt is formed when two ionic solutions are mixed. Okay, how do you know which salts are soluble and which salts are insoluble? The idea behind this is based on the solubility rule. Which ionic compounds are soluble in water and which are not, which are insoluble. These are the rules. Okay, if you take any compound that contains lithium, sodium, potassium, rubidium, cesium, ammonium. For example, it could be any anion. Anion could be anything, sulfate, chloride, bromide, any anion. Any compound like sodium chloride, sodium bromide, lithium bromide, any anion combination with these cations are soluble. Therefore, when they are dissolved in water, they are going to be soluble. You should be answering questions like, if I ask you whether lithium chloride is soluble or not, it's soluble because lithium is always soluble, lithium compounds, ionic compounds. Now this rule applies to all these three cations. Another rule that applies based on the, this is cation, M+. Cations, these two, there are 6 of them, cations. There are two anions. When they are found in the salt, regardless of whether what the M is, M+ ion, these, for example, if you take calcium nitrate, it is soluble. If an ionic compound is nitrate or acetate, it's soluble. Now, other things are very specific. If you have chlorides, bromides, iodide, and sulfate, they are soluble. Except, now this is based on exception. Only these 4 are insoluble. Therefore, anything else other than silver chloride, lead bromide, lead chloride, barium sulfate, lead sulfate, any chloride, bromide, iodide, or sulfate is soluble, except these are based on solubilities. These are soluble. This is kind of a soluble with exceptions. There are 4 exceptions for chloride, bromide, iodide. So you have to kind of, I will give you a list of these in your test. So you have to look up and find out. Carbonate are insoluble. These are based on insolubility. They are not soluble. And hydroxide. Carbonate, phosphate, sulfide, and hydroxide are insoluble, except these last 2 are based on exception. Lithium is soluble. There are 4 exceptions. Look here, there are 4 exceptions for chloride, bromide, sulfate. So therefore, you have to kind of analyze this and find out whether given an ionic compound is soluble or not. All right. So therefore, we can predict precipitation reaction. Right now, we're done with it. We gone over some of the ideas in last class period. So we move into new concept about chemical reaction. Electron transfer reactions are called oxidation reduction reactions. We're going to look into oxidation reduction reaction. Short name for these type of reactions are redox reactions. You take this and first we write and read part and the reduction oxidation. These reactions are called redox reactions. In these reactions, electrons are transferred from one atom in a compound to another atom in a compound. Normally it takes place between reactants. So reactants, if you have A plus B, let's talk about this later. In these reactions, one of the atoms in the reactant loses electron and another reactant atom in another reactant will gain electron. All right. So there's a short way to remember what is oxidation and what is reduction. This line is used for memorizing definition of oxidation and reduction. This line is Leo. It says, Leo says G. Leo stands for loss of electrons. Loss of electrons is oxidation. Leo, the last O is oxidation. G, last letter is reduction. Reduction is gain of electrons. For example, this is the reactant, one of the reactants. It loses 2 electrons, produce zinc 2 plus ion. So 2 electrons are lost from zinc. Zinc is said to be oxidized. Another example, the next example for reduction is copper 2 plus ion gains electrons. Gain of electron, this is gain of electron is reduction. This is loss of electron, loss of LEO, LEO. So this is the definition. What is our oxidation now? It's loss of electron. Reduction is gain of electron. So one atom gains electrons here, lost electrons. This ion or atom or ion, it could be either one, gains electrons in the reduction. We're going to give you a few examples. Single replacement reaction are reactions where one element is replacing another element in a compound. For example, if you react zinc with copper sulfate, what it does is zinc sulfate is formed and copper is given out. So this is single replacement reaction. This is how we do it. This is zinc. We put in a copper sulfate solution. This solution is copper sulfate. We wrote here. When reaction takes place, this is zinc. Copper 2 plus ion from this blue solution get deposited as copper metal on the zinc plate. As the reaction takes place, the color of the solution become less blue. That means blue color is coming from copper ions get reduced. So this is an example of most of the single displacement reactions are redox reactions. Some in this reaction, the zinc is dissolved. As the copper is deposited, zinc 2 plus comes out, forms zinc sulfate. Some of the copper ions from the solution are deposited on the metal. This is an example of redox reaction, single displacement. The blue color of copper 2 plus ions gradually disappears as the copper is deposited on the zinc. So we can write down oxidation. This is oxidized. Zinc is oxidized. Copper is reduced. So there are 2 electrons transferred between these 2 metals. In this case, zinc becomes zinc 2 plus, copper becomes copper 2 plus here. So this is an example of redox reaction, single displacement reaction. Now, let me tell you one thing. If redox reaction took place like this, direct transfer of electrons, there's no useful, it's not useful for chemistry. Redox reactions are used for producing electricity, electrochemicals. Therefore, we had to come up with a way where this copper and zinc are separated and create two electrodes to harness the electricity. Let me show you what I'm talking about. This one is the reaction I talked about. I wrote it clearly here. Oxidation takes place. Zinc 2 plus sulfate. Let me talk about oxidation number, increase, decrease in the next slide. To harness the electrons, we have to come up with an electrochemical cell. I am going to talk about it in a minute. Let me explain a little more about this reaction. This is the same diagram I have shown you. Oxidation number in a compound is the number, oxidation number is the charge on the element. If you look at zinc, zinc is neutral metal. Therefore, charge is 0. Copper in this compound is copper 2 plus. Because sulfate ion is 2 minus, copper need to have the charge balance. Sulfate is 2 minus as well. In this case, when this reaction takes place, zinc placed in copper sulfate, zinc oxidation number increased. It increased from 0 to +2. Normally we can say increase, if something increase oxidation number is oxidation. Reduction is opposite. Copper 2 plus become copper 0 here. Oxidation number, which is the charge on the ion, decrease. That means 2 plus became 0. So there are ways to find out which atom is oxidized or reduced based on oxidation number. So there are two half reactions here, where electron is lost, oxidation half reaction, and the reduction half reaction, where electrons are gained. Reduction is gain of electron. So this is the oxidation part of first one, reduction. In a redox reaction, always there's an oxidation and a reduction. Do you have any questions? Are you guys there? You guys okay? Hello? Anybody who can hear? All right. Do you have any questions?
No, sir.
Okay, I'm going to continue then. So to harness the electricity, electrons transferred in redox reactions, we come up with a way to isolate half reaction, redox half reaction from the oxidation half reaction. Electron flow over the wire from zinc to copper. We use a wire in this diagram below. If you look at this is the copper electrode, zinc electrode right here. We create a voltaic cell. When you design a diagram like this with two half reactions, this is the reduction half reaction, this is the oxidation half reaction. You use zinc and copper metal. Copper is here, zinc is here. This is zinc sulfate. This is copper sulfate. All right. So now the electrons that lost from the two electrons, which are given out from the zinc, passes to the wire, goes to here, complete the circuit, goes to this wire, copper, and passes through this. It comes here, complete the circuit. When there's an electron flow, this light bulb lights up. Therefore, this voltage type of cell, electrochemical cell, this is called electrochemical cell, could be used as a battery. So there are many types of battery. This is the first battery that we discovered, voltaic cell. This particular battery is called voltaic cell. This is a wet cell battery, wet cell. What do you mean by wet cell? These are liquids. This is not convenient. This is not convenient. What is a dry cell battery? The regular batteries that we use in our flashlights are dry cell. They don't have a solution. They have a paste of chemicals. We're going to talk about batteries in a little later. Now, how many of you understood that redox reaction could be put into a voltaic type cell, electrochemical cell, and used as a battery to generate electricity? And this is very useful. Therefore, there are many types of batteries: rechargeable batteries, lead acid batteries, dry cell batteries, alkaline batteries, camera batteries, nickel cadmium batteries. We're going to look into that in a later section. Summary. Oxidation is loss of electrons. There are two things that you need to know about reduction and oxidation. React and reduce. One that gain electrons helps to oxidize something, the other reactant. Therefore, reduce substance that copper is reduced. It is the oxidizing agent for zinc. Zinc is oxidized. It is helping copper 2+2 get oxidized, get reduced. Therefore, one that get oxidized act as an agent for reducing. One that reduced helps in oxidizing another compound. Therefore, reactant that is reduced in that reaction, copper 2+ plus zinc. Copper 2+ is the oxidizing agent. Zinc metal is the reducing agent. So we use this idea about oxidation reduction. This electron is transferred. Zinc is oxidized. We already know that. Copper is reduced. It gains. And when it gets 2 electrons, it becomes copper 0. When it gives electrons, it becomes, zinc loses electrons, it becomes zinc 2+. So copper is the reducing agent, as he talked about here. It helps. Let me get some water. I got a dry mouth. So zinc is the reducing agent. It helps copper to get reduced. There are other redox reactions. We talked about single displacement reaction before. Combustion, when something is burned in oxygen to produce water, etc., carbon dioxide, is a combustion reaction. Now, just like single displacement reaction, combustion reactions are oxidation reactions. There's a oxidation, loss of electrons, gain reduction in combustion reaction. Now, the idea about oxidation and reduction is not easy to apply for these reactions, combustion reactions. Let's look at this similar to the way we look at single displacement reaction. For example, combustion of methane. It could be propane, methane, coal, etc. We write the chemical equation. Methane is a hydrocarbon, burns in oxygen. Combustion is combustion reaction in which carbon dioxide and water is produced. Now it's very difficult to get the charges in here. How we know what is oxidation? Oxidation. molecular compounds are here. Therefore, there are no ionic charges. Therefore, we have to come up with a way other than looking at charges on the ions. What is oxidation? What is reduction here? Normally, when carbon goes to carbon dioxide here, it gains oxygen. GAIN. Gain of oxygen is called oxidation. So we use oxygen in this case to figure out which is oxidation. Carbon is oxidized to carbon dioxide. When a compound like methane loses hydrogen, right here, loss of hydrogen is also oxidation. So if you look at this, oxygen gains hydrogen here. Oxygen got hydrogen. This is gain of hydrogen is reduction. So water I cannot say anything else. This is loss of hydrogen is oxidation, gain of hydrogen is reduction. So alternative definition of oxidation reduction is oxidation, gain of electron or loss of hydrogen. Opposite is loss of oxygen and gain of hydrogen. So in reactions where you cannot use the ions to figure oxidation and reduction, for example, combustion reaction, we use the idea certain reactants gain oxygen, oxidize. Certain reactants, this for example, it become water. Gain hydrogen, that's gain hydrogen is reduction. Right here. So this is another way, without looking at electrons, you use oxygen or hydrogen directly. We're going to talk about that again. Using this alternative definition for combustion of methane, the gain of oxygen or loss of hydrogen is oxidation. The loss of oxygen and gain of hydrogen is reduction. In the following example, we discussed previously, methane and the product, oxygen, react to produce water and the carbon dioxide. So we can look at which one gain electron, which one gain oxygen, carbon gains. Gain of carbon gains, therefore methane gain oxygen, losses hydrogen. Therefore, carbon is oxidized too. carbon dioxide. Oxygen, J and hydrogen, that's reduced to. So therefore, this is the oxidation part, this is the reduction part, reactant which is reduced. Therefore, same analogy. Methane is the reducing agent. Oxygen is the oxidizing agent. Same idea we talked about in previous ionic reaction between metal and ions. There are 5 important redox reactions. Let me show you what they are. They are very common. Combustion, we talked about it. Gain of oxygen, loss of hydrogen. Therefore, burning in air, the products of complete combustion reaction where carbon dioxide and water is formed. Respiration. How many of you know glucose is converted to water and carbon dioxide in living organisms in the process called respiration? The carbon dioxide and water, for example, in human body is passed to lungs when we exhale. Oxygen is intake, taken into the body. This is an important redox reaction that take place in mitochondria. The cells have mitochondria which produce energy from respiration. They produce ATP. That reaction is a oxidation redox reaction. That's the second important. Metals like iron combines with oxygen to produce iron oxide, which we call rust. Silver metal, silverware, in the sulfur compounds in the air produce silver sulfide. This is black color that produces silverware. This is just like formation of iron oxide. This is an important redox reaction, rusting, tarnishing. For example, burning potassium to produce potassium oxide. This is metal with the oxygen, just like rust. Rust is this reaction. This reaction is called rust formation, where iron reacts with water. The bridges get corroded. Corrosion is a process where the rust is this formula. This is third important type of reaction. Bleaching also is a redox reaction. Sodium perchlorate contains this ion, ClO ion. That ClO ion breaks up to chlorine, plus oxygen. This oxygen react with chlorine and oxygen react with and make them wider. The dirt in the clothes are removed, then the clothes become whiter. That's the bleaching. So these are four important redox reactions. The last one is, I talked about it. When you make up electrochemical cell like voltaic cell out of redox reaction, it could be used to get electricity to power lights, to heat. There are many applications of electricity. Therefore, batteries are used even in driving in electrical cars. So lithium batteries. Now there are 5 important types. If I ask what reaction is redox, if one of these 5 are there, that's a redox. Precipitation reaction, acid-base reaction are not redox reaction. So you have to see which one are redox reaction. Single displacement reaction are combustion, respiration, rusting, bleaching, and batteries are examples of redox reaction. Now we finish redox reactions. Now we are moving on to chemical calculations. It's difficult to write here. Chemical calculation. Chemical calculations are when you use a chemical reaction, A plus going to C. You use certain grams of A, certain grams of A, certain grams of B. Let me write Y grams of B. C grams of. Now, if you start with certain grams of A, you should be able to calculate how many grams of C is produced. That's a chemical calculation using reaction, chemical reaction. So to do this, first you have to come up with the formula mass. Formula mass of A. For example, how do you get formula mass of water? You look in the periodic table. That's 2. the atomic mass of water is 1.00. You can look up in the periodic table, find that out. This is 16. There are 2 water molecules. Therefore, this is going to be 2. When you add them up, it becomes 18.0. These are normally given in atomic mass units. This 18 formula weight of an ion molecule is also expressed in grams per mole. We're going to talk about. So we have to know how to calculate formula weights to do the chemical calculation using chemical reaction. Formula weight, therefore, is an important first step in chemical calculation. Formula mass or weight is obtained by adding sum of the atomic weights in atomic mass units of all compounds in atom or in compounds. Formula. Compound is like carbon dioxide. Atoms is like carbon. You can find out formula is carbon is 12. It's carbon dioxide is 44. You add 12 times 2, 16. 32 plus 12 is 44. That's how you get it. This is the ionic compound right here. This is a covalent compound. Regardless of what they are, these are based on bonding. This is the formula. This is the formula of water. This is the formula of aspirin. Aspirin is taken as a pain reliever. So how do you calculate the formula mass? You add all atomic weights. You look in the periodic table. It is this number. This is also called grams per mole. I'm going to talk about this in a minute. Right now, atomic mass units are okay. So when you add them up, 23 plus chlorine's atomic weight, you get 58.5. In a complex formula like this, you have to calculate the number of atoms. There are 1 nickel atom. This is the nickel's formula mass. Nickel is an atom with formula, chemical symbol, 58.7. There are 2 chlorides. So you multiply by 2, 35 is the atomic mass of chlorine. And you add them up. This is continued. There are 12 hydrogens here. How do I get 12? This 6 multiplied by 2. The subscript shows how many atoms of hydrogen. 6 times 2 is 12. Therefore, 12 hydrogen. Now, there are 6 oxygens. How do I get 6 oxygen? 6 here. There's no subscript. 1 is 1. Therefore, 6 times 60. Then you get the formula mass. Like I said before, it is also grams per mole. I'm going to define that in a minute. In a molecular compound where there are no ions, formula mass, these are both formula masses, formula weight. It could be called formula weight for ionic compound and molecular compound. But sometimes we call molecular weight. Molecules are only present in molecular compounds. Therefore, if I say molecular weight of a compound, that means it's a covalent molecular compound, covalent bonded compound. So you know how to get the formula mass or formula weight. Formula weight can be used for either ionic or molecular compound. It tells nothing about whether they are ionic or molecular. Formula weight is generic name for formula mass. But molecular weight is just used only for covalent compound. Molecular compound is, molecules are covalent compounds. Covalent. In this course, in the text, formula weight is normally for ionic and covalent compounds. Molecular weight is only for covalent compounds or molecular compounds. Now, we know how to calculate the formula weight now, or molecular weight for molecular compounds, covalent compounds. Molecular weight. Now we are trying to get into more chemistry. When you write an equation, for example, hydrogen plus oxygen produce water. So what you do is put a 2 here, 2 here. Equation is balanced. When you balance the equation, these numbers are called stoichiometric coefficients. 2 here, 1 here, 2 here. What are stoichiometric coefficients represent? They represent atoms, molecules, or ions. I cannot write to you. This is a molecule. This is a molecule. Sometimes it could be sodium ion or whatever. So these numbers are represent mole, molecule. Right here. They are all molecules. But we cannot pick up molecules. We cannot never pick up molecules. We use a concept called moles. Mole is a large number of molecules. Mole is a 6.02, 10 to the 23. Molecules, collection of that many molecules, mole. Mole, when you use a mole, we can see them. See hydrogen. If you cannot look at one molecule, they are invisible. So mole is used in chemical reaction. What is a mole? This is the amount of substance. There are 2 moles of hydrogen here, 1 mole of oxygen, 2 moles of hydrogen. This could be molecules or moles, but we use the moles. Molecule is too small. Mole is collection of atoms, molecules. Amount of as many atoms, molecules, and ions. If you take carbon-12 isotope, carbon is 6. This isotope atomic mass is AMU. Atomic mass is AMU. If you take atomic mass in grams, it has 1 mole of carbon-12 isotope. Carbon-12, 1 mole of carbon-12. Therefore, we call this molar mass of carbon-12. Molar mass is 12 grams per mole. So grams per mole and AMU is same is equal to each other. But AMU is not so useful. So we use molar mass. AMU is not molar mass. Formula mass, molecular weight. Molar mass is mass of 1 mole. A mole is important concept in chemical calculation. Whether mole is iron atoms, mole of iron atoms, mole of methane molecules, mole of sodium ions. Sodium ions is that's CH4 or Fe atoms. They all contain same number of formula units. For example, 1 mole of iron atoms contains 6.02 10 to the 23 iron atoms. It could be sodium ions. It could be, what is the other one? CH4. 1 mole is formula mass per gram per mole. You take formula mass in grams, formula mass, formula weight, FW or molecular weight in grams. That's a 1 mole. This number, which is 6.02 to 10 to the 23, is called Avogadro's number. Avogadro number has been measured experimentally. Why we are using Avogadro number is to get enough quantity that we can see. And do chemical reaction in the lab. You have to, being human, we need to see the material. We cannot just look at one molecule or ion. So it's like 12 eggs are used to collect eggs so that we can handle not each egg individually. We don't count eggs one by one, 12. So we count atoms by the Avogadro number. Therefore, Avogadro number is also called chemist dozen. It's like a quantity large enough so we can handle chemical reaction. A mole is obtained by taking formula weight in grams, which contain 1 mole of that formula mass. The value is how many units of atoms or molecules or ions in 1 mole of that material. The molar mass is obtained in grams. You take the formula mass, formula weight, molecular weight in grams, you get molar mass. For example, glucose is C6H12O6. You add atoms. How do you get that one? 6 carbon added up with 12 hydrogen plus 6 oxygen. When you get the atomic masses, hydrogen is 1, carbon is 14, oxygen is 16. You get 180. It's called grams per mole, or AMU. See, this is AMU. AMU is useless in chemical reaction. What we use is grams per mole. 1 mole of glucose has mass of 180. 1 mole is molecular weight taken in grams. Urea, similar story. Molecular, molar mass is formula weight, molecular weight. Weight is 60. Molar mass. See, this molar mass, once a gram per mole is, that's a molar mass. So 1 mole of urea contains 60 grams of urea. I am going to continue this one because I need to finish chapter 4. You guys need to go somewhere, come back and watch rest of it. Okay, I'm going to continue this because I need to finish this one. I am going very slow because you need to understand. Okay? I am going to put that on canvas. I'm going to continue this. If you guys have to leave, you can come back and watch the, it's going to be a couple more slides. All right? Do you hear me?
Yes.
Okay, if you want to hang around and listen to me, that's fine. How do you convert moles to grams? Using molar mass. I said molar mass is grams, number of grams in 1 mole of substance. How do you convert moles to grams and grams to moles? There are relationships between molar mass, grams, and moles. We're going to look into this. I need to read this. We can use molar mass to convert from grams to moles, moles to grams. So if you take a grams of a material, compound, or atoms, in the chemical equation, conversion factors are there. For example, they are in moles. In chemical equation, hydrogen, oxygen, water. There's no two there. Two there. These are moles. 1 mole here. 1 mole here. We start chemical reaction in grams. How do you convert to the moles? We normally follow this procedure. Grams divided by molar mass. Or how do you convert moles to this? This is grams mole. Moles multiplied by molar mass. You get the grams. So let me show you this. This is grams. This is grams converted to moles. So this is what I use to get the moles. Do you see that? If I want to convert something back to moles, moles to grams, this way, you multiply moles times molar mass. So these are basic idea how you convert moles to grams using molar mass. For example, if you take water in this reaction, 36 grams of water. How do you convert it to moles? Grams divided by molar mass. This part is 1 over molar mass. Normally molar mass is for water is grams per 1 mole. This is molar mass. This is the inverse of molar mass. This 18 is at the bottom. This is factor-label method. You have to cancel grams of water to get the moles of water. That's how we do the calculation. So what we do to convert grams to moles is grams divided by molar mass. We use that idea. So in chemical calculations, we use this equation. Moles of, here we calculate moles of 36.0 grams. Grams divided by molar mass. This is conversion factor used to cancel out the units to get the moles. Factor-label method. So this one is other way around. How do you convert 2 moles to grams? You start with 2 moles. Moles times molar mass. To get the grams, this relationship. To get the grams, molar mass times moles. Moles times molar mass. That's how you get grams from moles. These are pretty easy calculations. Let's see how you get moles and ions. Grams to, this should have been grams to moles, then the ions. Let's see. Example. Sodium sulfate, ionic compound. They're asking, if you are given 5.63 grams of sodium sulfate, how many ions are, how many moles of ions? Moles of ions. Grams to ions and moles. They're asking, how many moles of sodium sulfate are there? How many moles of sodium ions are there? How many moles of sulfate ions are there? These are the questions. How many formula weight units? How many sodium ions? How many sulfate ions? We can answer all these questions, ions and moles. First, you have to get the formula mass. Formula mass is converted to formula mass is when you add it up, all the atoms, 142.1 AMU. Now the molar mass is same, 142.1 grams per mole. Formula mass is AMU, atomic mass unit, as given in the periodic table. So therefore, 1 mole of sodium sulfate is 14,142. This is same as molar mass. So how you get the moles of sodium sulfate? This is, remember we wrote last time, moles is grams divided by molar mass. Therefore, we write down this equation. This is moles. That this is 1 over molar mass right here. We use the factor label method to cancel sodium sulfate grams here. We end up with how many moles of sodium nitrate are there in that many grams? This many grams have that many moles of sodium. The question is not formula units. This is called how many formula units, how many moles of formula units. That's the whole thing. There's some sodium ions. Each sodium sulfate contains 2 sodium ions. The conversion factor is 1 mole of sodium sulfate is equal to 2 moles of sodium ions. So that conversion factor is used to get sodium ions. There are 2 sodium ions. There are 1 sodium ion for each sodium sulfate molecule. Therefore, answer asking for sodium ions. Therefore, you use this factor. 2 moles of sodium ion is in 1 mole of sodium sulfate. This cancel out. You get twice as many sodium ions. This is the twice the number right here. There are 0.0396 times 2. You get the number of sodium ions. We are just playing around with grams to moles. And how many ions? Once you get the moles of formula mass, you can calculate, look at the formula and how many ions are there. That many ions are same moles of formula weight. This is sodium sulfate, it's formula. It has 2 sodium ions. Therefore, we multiply here by 2. We're going to do another calculation. The previous calculation was about ionic compound, formula mass, formula weight. Now you're going to talk about molecular weight and molar mass and number of molecules, atoms, molecules and atoms. Aspirin, which is a covalent compound. These are non-metal, 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 3 non-metals forms. You can calculate the formula weight. We calculated that. It's happened to be 180 AMU. Molar mass is grams per 1 mole. We normally don't write the 1 here, right here. Just a 1 in there. So what is the question? In 3.60 grams of aspirin, how many molecules of aspirin are there? There's a 1 molecule. It's same as how many formula units in ionic compound. How many moles of aspirin are in 0.360 grams? Now the grams divided by molar mass. This is 180 is the molar mass here. So this is grams multiplied by 1 over molar mass. You get 0.00200 aspirin moles. So this is a mole. Mole is 1 time 6.02 10 to the 23 molecules. Whatever the unit, this is molecule. 1 mole of formula units is also that many Avogadro number of units. It's a 1 mole. Therefore, if 1 mole contains this many, 0.00200 would be Avogadro number multiplied by that Avogadro number multiplied by 0.0020. It's calculated here. Each mole of aspirin contains Avogadro number of molecules. Therefore, basically 0.200 multiplied by 6.02 10 to the 23 is the answer. This is moles multiplied by Avogadro number. Avogadro number is 6.02 units. It could be ions, atoms, molecules. 1 mole. See, this is 1 mole here. Molecules, in this case aspirin. That's the definition of mole of molecules. It could be moles of formula units. Therefore, you can calculate how many molecules are there. Now, let me explain something further. There are 9 carbon atoms, C9. How many carbon atoms are there? That number multiplied by 9. Each unit contains 9 carbon. Therefore, if someone has this aspirin sample has that many molecules, how many carbon atom moles? Then you multiply this number by 9 to get the hydrogen atoms, number of hydrogen atoms. you have to multiply that by A. For oxygen atoms, this by 4. Subscript shows how many atoms are per each molecule. Now we're going to tie all these up in what we call stoichiometry. That's a fancy name for this idea, calculation using chemical reaction. What we calculate is you start with grams of reactants, convert them to product, convert them to moles, then convert them moles of reactants. Reactants is normally A. Let me not get bogged down there. So chemical calculation using chemical reaction is called stoichiometry. Using the relationship in mole relationship. Following is an overview of the type of calculation when a reactant goes to products. Reactant or reactants go to products or products. Let's look at the simple chemical equation. This is 1. Molar ratio is 1. When you convert 1 mole of A, it ends up with 1 mole of B, 1 to 1. Now, we normally in a lab, we start with grams. We end up with grams of products, or B, grams of reactants is A. To use the calculation, this is stoichiometric coefficients show only the molar ratio. I cannot write. Molar ratio is 1 mole of A is equal to 1 mole of B. So what you start with is grams. Grams divided by molar mass. Remember, you get moles of A. This is the grams of A divided by molar mass of A. Then you use the coefficient in the balance equation to do this is the conversion factor. You can use this as a ratio. 1 mole of A is equal to 1 mole of B. This gives 1 use here, you end up with 1 because this is 1 to 1. Now you have to get the grams of B. You got the moles of A converted to moles of B through the conversion factor. So how do you get the B gram? Mole times molar mass is grams of B. We wrote down those before. Grams, moles is equal to molar mass. So if you want to calculate molar mass, grams, if you want to get the grams, grams is equal to molar mass times moles. That's what I wrote here. Molar mass times moles. Get the gram. So you can do, this is kind of a theoretical calculation. We didn't use the numbers. So you can easily do a stoichiometric calculation. I wrote up the relationship again, typical stoichiometric calculation. Grams to moles. Let's go through an example. Nitrogen. How many grams of nitrogen are required to produce 75 grams of ammonia? Now you start with nitrogen grams. You start with ammonia grams. You are asked how many grams of nitrogen will produce this. How many grams of? So you first thing, balance the equation. You have to write the chemical equation. How do you write the chemical equation? Nitrogen plus hydrogen is going to ammonia. Then you have to balance. Balance is 3 here, 2 here, 2 here. Stoichiometric coefficients are 2, 3, 2. See, I balance the equation. This is the equation. There's a 1 here. Remember, always, if there's no number in front of the chemical, there's a 1 stoichiometric coefficient. So you start with 75.0 grams. So you start with, like we did, 7.05 grams of ammonia, converted to moles of ammonia. Then the ammonia converted to moles of nitrogen, and moles of nitrogen to grams of nitrogen. See how the pattern, grams to moles to different products, grams of nitrogen. So that's what we'll be doing. How many moles of that? That's the question. This is grams 1 over molar mass of ammonia is 17 molar mass. You get number of moles of, this number is 441. When you divide 7.50 divided by 17, last time I did that, I got 444. 0.441. You can check it out. So this number is 441 moles of ammonia. So the question is, how many moles are from moles? Use the conversion factor. 2 moles of ammonia is equal to 1 mole of nitrogen. So we use the conversion factor, which I obtained from these two numbers. 1 to 2. This is same thing. This part up to here is equal to that. So it divided by 2 now. 0.22. 4. This number 4 divided by, okay, you can calculate yourself. That's how many moles. How many grams of nitrogen? Nitrogen is 28. 14 times 2. So let me do this. Multiplied by 28. 6.17 grams of nitrogen. I completed this reaction. I got 6.176 rounded off 6.18. Now this is the type of stoichiometric calculations you will be doing. The practice, another one. Mass of aluminum oxide is required to prepare 27 grams of aluminum. This is the reaction. Aluminum is produced from aluminum oxide called bauxite through electrolysis to produce aluminum. This is done in Quebec, where the hydroelectric power is Canada. Abundant. Electricity is abundant. So they produce a lot of aluminum. Aluminum cans are produced from aluminum and different engine parts. So you start with 27 grams of aluminum. So you convert this to divided by molar mass, moles of aluminum. Then aluminum moles, 1 mole of aluminum moles is 1 to 1 here. Oh, this equation is not balanced. I'm sorry. 2 here. Let's balance this. You have to put a 3 here. 3 here. How do you balance this equation? There are 2 oxygens. Let's put a 2 here. That nitrogen is balanced. So you have to put oxygen to balance. 3 here becomes 6. Then 2 here. It becomes 4 here. So now it's balanced. Let's finish up the let's come back to this in a minute. There are another question. What did I write? 3 here. Two here. 2 here. 4 here. You start with 27. Convert, this is the aluminum molar mass divided by molar mass. Then 1 aluminum, 1 mole of aluminum is 4 moles of aluminum. This is a mistake here. 4 moles of aluminum here. Therefore, 4 here. This is wrong. 2 moles of. This is the molar mass of AlO2. This is moles multiplied by it. So you get this number. So this is kind of a divided by 2, you get 1. This number should be divided by 2. Why? Because there's 1 and 1. This is 1 to 4 become 1 to 2. This is this number divided by 2. 51 grams of aluminum. I found a mistake in this came up. This question comes with the slide. Publisher gave. There's a mistake in this balancing. Do you agree with me? This is 4. This equation was not balanced. You had to use the balance equation. If you apply this to carbon dioxide, ammonia, urea breaks up with water to ammonia and carbon dioxide. Urea is a fertilizer, same as ammonia. It produces ammonia after breaking up. So question is, how many moles of urea? How many grams of each carbon dioxide and ammonia produce when you break up? Moles of ammonia here. So if you start with 1 mole of the reaction is balanced, right? You have to first check that. One carbon is correct. How many oxygens are there? 2 oxygens. That's correct. How many nitrogens? 2 nitrogens. That's correct. 4 hydrogens plus 2 hydrogens, 6 hydrogens. 6 hydrogens. 2 times 6 hydrogen. That's equation is balanced. Therefore, there's no mistake there. So you start with 0.83 moles of. Now convert it to 1 mole of ammonia. That's the conversion factor. Is equal to 2 moles of ammonia. So ammonia is molar mass here. Moles times molar mass, you get the grams, 28 grams. So you can calculate the carbon dioxide. Carbon dioxide is similar. Carbon dioxide is 44. Conversion factor is 1:1. Therefore, it should be half of this and multiplied by 44 for the carbon dioxide molar mass. It should be down there in the next slide. It's not there. Therefore, how many grams of carbon dioxide produce? 0.83. This is 1:1. 1 carbon dioxide mole is converted to 1 carbon dioxide mole, 1:1. Therefore, it is multiplied by 1 multiplied by 44. 44 is, let me finish it, 0.83 multiplied by 44. So I get 36 grams of carbon dioxide, 36.5. Okay, that's how you do the calculation. Now I wanted to tell you about limiting reactor in a chemical reaction. This is another idea. Chemical reaction has limiting reactor. If you have only one reactant in the chemical reaction, limiting is A itself. If you have 2 reactants, this is B. It depends on, this is 1:1 mole, how many moles of A or B. If one of them is limiting, that means used up first, it limits the number of grams of C. Now, how many of you heard about when you follow a recipe? Ingredients limits what you can get from following the recipe. For example, when you make hamburgers, assume I put 2 patties in a hamburger, bun and 2 patties. If you have 8 buns and 4 patties, how many hamburgers I can make? It's limited by this. Only 2 buns are used. Therefore, left over 6 buns. In this case, limiting ingredient is the patties, beef patties. So it limits double burger. Just like that, chemical reactions are recipes Just I assume they are recipes. So they follow the limiting factor, just like the patties when we were trying to make hamburgers. Limiting ingredient or reagent. Reagent is the reactant. One of the reactant reagent is also called reactant. Reactant that is used up first in a chemical reaction. Limit the amount of products you get. For example, if you have nitrogen and oxygen reacting to produce this is 1:1. That's the recipe ratio. Chemical reaction is the recipe ratio, 1:1. If you start, this reaction is balanced. If you start with 5, this is a 1 mole reacted, 1 mole gives to 2 moles of nitrogen oxide, monoxide. Before the reaction, this is the amount. So 5 moles, 1 mole. At the beginning, there's no product before the reaction. If you look at this, can you see nitrogen are in excess, like hamburger buns? This is used up first. After the reaction is 0. That's the limiting reactant. Limiting reactant is the one reactant used up first. Therefore, this is the excess. This is limited. So it's important to use the limiting reaction in the stoichiometric calculation. When you calculate, we use 1 moles of oxygen is equal to 2 moles of NO. You don't use nitrogen because it's excess. In this experiment, 1 mole of oxygen react with 1 mole of nitrogen, leaving 4 moles, the 4 moles here. Oxygen is used up first, is the limiting reagent. 4 moles of is called the excess reagent. When you have 2 or more reactants, if they are in stoichiometric ratio, 1 mole ratio, then both are limiting reagent. Normally in a lab, when we do reaction, for example, when you burn methane in oxygen, what is the limiting reagent? Oxygen is plenty. We run out of methane. Therefore, it's easy to find out in combustion reaction. Fuel is the limiting reactant. There are plenty of oxygen. If you put something in water, like sodium, produce sodium hydroxide. Sodium is limiting. There's plenty of water. So you can say there are excess by default, by nature. Some reagents are excess. Idea is we have to use to calculate the amount of sodium hydroxide in this reactor. You have to start with limiting reactant, methane or sodium. Suppose 12 grams of carbon is mixed with 64 grams of oxygen. and following reaction take place. Carbon plus oxygen produce carbon dioxide. That reaction is balanced. What do you think the excess? Normally excess is oxygen. Why? The carbon is cold. Compare which is the limiting reagent. In this case, if you look at molar ratio is 1 to 1, 1, 1. You start with 12 grams, 64 grams. This divided by 12, you get 1 mole. This divided by 32, you get 2 moles. In this case, 1, 1 ratio. If this is converted to, you will have one of these going to one of these. Therefore, 2 minus 1, you have 1 left over. So after the reaction, excess reagent, 32 grams. Now when you calculate products, carbon dioxide, you use the conversion factor, 1 to 1, in this case, 1 to 1 both. Anyway, some reactions, these ratios are not equal like this. Did you get the idea about limiting reactant? Sometimes you use the limiting reactant to convert reactant to products, not the excess reagent. I'm going to continue since only few slides. The efficiency of a chemical reaction is measured by percent yield. There are 2 yields in a chemical reaction, both in grams. Actual yield is when you go to the lab, do the experiment, you physically do the experiment and isolate products. That's the actual yield. Theoretical yield is stoichiometric calculation, as we done here. You start with grams of, theoretically, when you use a chemical reaction, you're not doing it. You are just thinking about so many grams of reactants. Then try to get how much grams of product you get. This is the actual yield of the product. This is always, actual yield is less than 100. If you start with 100 grams, theoretical yield, you are supposed to get 100. If you are supposed to get 100, this is less than 100. This is 100. There always actually is less than theoretically. If you do an experiment, you get 60 grams of actual yield. Calculated yield is 80 grams. So what is the efficiency? Supposed to get 80. Therefore, 60 divided by 80 multiplied by 100. You get 6 divided by 8. Only 75%. Yeah. If a person is meticulous, reaction is complete, clean reaction, you can get close to 95% easily. If the person following the procedure is sloppy, it could go down 60%. So therefore, yield also shows how efficient you are doing the reaction. Also depend on the type of reaction. Certain reactions have byproducts. Therefore, you don't get 100% yield. If you are in a chemical industry or in the industry, you try to find reactions, most efficient reactions, which practically give close to 60%. Should be good for chemical industry. But 40% of waste could be byproducts that needed to be taken care to prevent environmental pollution. Therefore, efficiency shows so many things. How good the reaction is, how efficient you are in the lab. Also, how to avoid production of byproducts, unwanted products, which cause pollution in the environment. Suppose we react 32 grams of methanol with excess carbon monoxide. Obtain, that's the actual yield. Calculate the table. Obtain means practically we got it. You have to write the reaction. CH3OH. Excess carbon monoxide. Acetic acid is okay. Let's see, they probably write the reaction here. This is balance. 1, 2, 1, 2. 4 is 4. This is a stoichiometric coefficient 1. You start with 32 grams. Molar mass is given as 32. Therefore, 1 mole. 32 divided by 32. Excess is said to be, therefore you don't use this one to convert to products. Use 1 mole. Produce 1 mole right here. Theoretical mole. These are calculations. So acetic acid is molar mass is 60. 1 mole is 1 mole times moles times molar mass grams. Actually, it's 55. Now, how do you calculate theoretically? 50 divided by 55 divided by 60 multiplied by 100. This is 92% yield. That's how you calculate percent yield. we already talked about these things. Kinetic energy is a form of energy. We have potential energy, kinetic energy. Kinetic energy is energy due to the motion of an object, energy that object process when an object is moving, when it brought to a stop. Its kinetic energy is obtained. Heat is a form of kinetic energy. Heat is motion of particles, motion of atoms, molecules in an object, making up the motion. When two objects are brought together, they collide at the boundary. The temperature low, cold, temperature is high here. Thermal equilibrium is reached when the object two objects came to the same temperature. Heat is commonly measured in calories. 1 calorie is amount of heat required to increase the 1 gram of. We talked about this in chapter 1. The SI units for heat is kilojoules or joules. 1 calorie is 4.18 kilojoules, 10 to the 3 kilojoules. 1 calorie is negative kilojoules. Kilojoule is bigger. So how do you calculate the heat absorbed by certain things? You use the specific heat. Specific heat of water is 1 calorie, same as amount of water increased by 1 degree Celsius, 1 gram of water. Water has specific heat of 1. Water has the highest specific heat. We talked about it. How do you measure heat is release or gain during object temperature is changed. Specific heat of the object, mass of the object, final temperature, initial temperature. Final temperature, that's the initial temperature. So amount of heat absorbed by 32 grams of water by increasing temperature from 23. That's the 23 initial, final. That's the mass. Water is 1 calorie per degree per Celsius. So if the temperature goes down, this quantity is negative. So this, if that goes from 95 to 23, this amount of heat is called negative heat. Negative heat is heat absorbed, heat given out is called exothermic. Exothermic. How did I jump here? This is endothermic. Heat is absorbed. That's how you calculate. Specific heat times mass times temperature drop gives you the heat absorbed or release. I'm stuck here. Okay, let me go back to, okay. Exothermic reactions release heat when a potential energy higher, when you fall off, water fall off. This is a energy release. The potential energy of chemicals are in bonds. Bond energy is potential energy. We talked about it. So potential, just like potential energy falls, energy is released. When you burn methane in oxygen, potential energy in the bonds are released. The bonds have higher energy in carbon-hydrogen bonds. 4 of them. Carbon-oxygen bond, 2 of them. When you produce carbon dioxide, carbon-oxygen bond, carbon-hydrogen bonds, oxygen bond. There are 4 of them. There are 2 of them. These bonds are low energy, have less energy than the bonds in here. Therefore, energy is released when methane burns. This amount of energy per reaction is 1 mole of methane is burned according to the equation right here. Produce carbon dioxide and water. We gone through this reaction. At the same time, you write down delta H, heat of reaction, heat of combustion, is delta H is equal to negative 802. This is the amount of negative. So in a chemical reaction, we put that carbon dioxide, water, put a parenthesis, and write down heat of reaction. So this is the conversion factor. This need to be negative. Then we end up with negative energy. Burning 1 mole of carbon methane, which is molar mass here, 16 grams of methane produce this. Therefore, in a chemical reaction, we can calculate the heat given out just like the grams of the product. This is the delta H for carbon oxygen reaction. This is positive endothermic reaction. Endothermic reaction, one that absorbs heat. Positive means absorption. This is positive. Heat of combustion is normally exothermic. Endothermic reactions are like this, positive. So we can calculate heat given off or absorbed using chemical reaction. This is energy in chemical reaction. For example, this reaction, the heat is part of the reaction. Just like the products, heat is part of the reaction. It's called thermochemical equation. When a chemical reaction has delta H, it is called thermochemical chemical equation. Now, to calculate heat given out in a chemical reaction, you have to balance the reaction. Normally, balance equation is the one that we give here. If you have sulfur trioxide, to balance, sulfur is balanced. Now, if you look at this, there are 2 here, 3 here. To balance that, you put this is tricky. You start with the oxygen. You put a 3 here, 2 here. I'm going to run in. This is balanced in the below. I shouldn't be worrying about it. So you start with 2 here, you put a 2 here. So there are 4 here, 6 here, put a 2 in, 1. 4, 5. 4 plus 2, 6. 6 is balanced. This is the balance equation. So how do you calculate heat? You start with grams of sulfur dioxide. Normally, oxygen is excess. So you start with, this is the molar mass of sulfur dioxide. Grams divided by molar mass here. Get the moles of sulfur dioxide. Two moles gives this. This is the 2 moles. This is calories. So when you do the conversion factor, you get negative 702 kilojoules. Okay, that's how you calculate heat in chemical reaction.